Hey guys, here with Zero Code NFT here. Today I would like to talk about the ERC721A, also known as Azuki smart contract. For those of you who haven't heard yet, Azuki smart contract promises to reduce the gas fee for minting to the point where if somebody mints 2 or more NFTs in one transaction, one batch, it will essentially cost the same as minting one, which sounds pretty awesome. But as with everything, this approach also has its own pros and cons. So in today's video, I would really like to just go over this smart contract and help you figure out if this type of smart contract actually makes sense to use in your next NFT drop. So let's dive in. Okay, let's see here. So I went to the azuki.com ERC721A, and as they are saying here, the Azuki smart contract will enable minting multiple NFTs for essentially the same cost of minting a single NFT. And they're giving the context here and also the measurements, how they arrived at these gas savings. So what they did is they compared their smart contract to the OpenZeppelin's ERC721 enumerable. For those who don't know, OpenZeppelin offers a collection of smart contract templates or like presets that a lot of developers use for their development. Not only in NFT, but other types of smart contracts as well. But anyway, so that's the contract they used for comparison. And as you can see, the gas savings are substantial, even though, in my opinion, this is a little bit exaggerated because not everybody uses ERC721 enumerable extension. Personally, I don't use it in my contracts. But nevertheless, I appreciate the work they did here. And I think this smart contract variation definitely has its use. So let's see how does it actually reduce the gas fees. So the first optimization they did is removing duplicate storage from the OpenZeppelin's ERC721 enumerable. What this means is that they just found some redundant storage usage and they removed it. And if every time you save something on the blockchain, it costs gas. So by removing this redundant storage, we're saving on gas. So that's optimization number one. Then optimization number 2 is updating the owner's balance once per batch mint request instead of per minted NFT. What this means is, let's say, for example, if I minted 2 NFTs in a particular NFT collection, and then after some time I came back and I want to mint 5 more. So traditionally what would happen is, as you mint these 5 more additional tokens, your balance would be updated on every step. So like if you minted token 3 and then your balance becomes 3, you mint token 4, your balance becomes 4, and so on and so forth until you reach 7. So what Azuki are saying is, if we already know that this person has 2 tokens already and we know that they want to mint 5 more, why do we need to update his balance every step of the way? Why don't we just, skip all this gas wasting and we just update his balance directly from 2 to 7? Which makes a lot of sense. And that's where the gas saving comes from. And then finally, the third optimization is updating the owner data once per batch mint request instead of per minted NFT. This is probably the most complex to understand, but also probably the one that offers the most savings. So what they're saying here is, we don't need to explicitly set the owner on every token ID. We can imply who is the owner just by looking and iterating through these tokens. So like, for example, let's say we don't know who Alice or Bob are. We just want to know who is the owner of token 103. So we look it up and it so happens that the owner of 103 is actually explicitly set. It's Bob. So we're done. We know Bob is the owner of 103. We're done here. But then what if you want to see who is the owner of 102 and we check token 102 to give us the owner and the owner is not set. So what we need to do now, we have to iterate back down until we actually find the token that has the owner set explicitly, because in that way we can say that all those other tokens along the way were also this person's. So like we will go check 102, owner is not set. We'll check 101, owner is not set again. Then finally, at the token of position 100, we see that it has Alice's address as the owner. So that means, that Alice is also the owner of 101 and 102 as well. That way we can tell, but it does require us to do these iterations back until we find the owner at some point. So, like for example, if if let's say Alice was actually instead she was explicitly set as the owner on a token number 90, and we're checking token 102, that means we would have to make 12 steps back until the token ID 90, where we'll actually find Alice's address. And that way we can say that, all the tokens that came before that were also hers. So that's the way it works. But they're also saying here that this optimization involves some additional logic, especially when it comes to transfers, but this is beyond the scope of this blog. So that's where I would like to actually dig a little deeper. And to do that, we will go to Azuki's GitHub repository. This is where they actually have their source code. And somebody raised this issue here where they're saying gas fees very high on safe transfer method. Safe transfer is invoked anytime you transfer tokens. So for example, if you're sending your NFTs to someone else directly, or you're transferring through OpenSea, this method is called. And what this person is saying that they minted 310 tokens in one transaction, in one batch, one big batch of 310 tokens. And they're saying that when they were transferring tokens closer to the index 0, like token 1 or token 2, 3, or 4, the gas fees was not bad at all. But as they were getting to the tokens like 300 and more, the gas spiked to $300. So they're raising a very valid question here. And the explanation to that is, lies in this ownership of function that we looked at earlier, that third optimization. Because if you remember, in order to see who is the owner of a particular token, if he's not explicitly set, we have to go all the way back, enumerate until we find a token that has an address assigned. So it makes sense, like if you're transferring token number 5 and the owner is not explicitly set, then we're enumerating back until we reach token 0, where this owner is set. So we only have to make 5 iterations to find out who is the owner. But if you're now transferring the token with ID 300, that means you have to make 300 steps back until you actually find out who the owner is, and that way you can assign a new owner. So that's why the big batches like that cost more. So here they also, in a discussion, they are saying that the golden middle is 8 tokens, where you have a good balance between having like a reduced or a mint cost, but also not having transfer costs that would break the bank. So if you were to use this smart contract, you have to consider, how do you plan to, what kind of batch sizes do you plan to allow your minters to do? Like if you're only going to limit people to, let's say, 10 tokens at most in one transaction, then you're good. It makes sense to use this contract. You'll see a lot of gas savings on minting. But if you are allowing big batches like 50 or 100 tokens, then you have to be aware that they will still have cheap gas fee as they're minting, but then when the time comes to transfers, they might see higher transfer fees. So that's the biggest consideration you have to do when you are considering this type of NFT smart contract. If you are looking to launch your NFT collection without writing any code, do check out Zero Code NFT. It's a no-code NFT launchpad created by me and my team. It allows you to drop your collection without writing zero code. And we actually did add Azuki variation of the NFT contract into our no-code smart contract builder. So if you're interested, please go ahead and give it a try. It doesn't cost anything to start. You don't have to pay anything to test. You only pay once you're ready to deploy to the mainnet. With that, I hope that this video was helpful. If you have any questions, feel free to drop them in the comments or join our Discord. And I'll see you in the next video. Bye.